This video is going to cover number 7 and number 10 in your Kinematics problems worksheet packet. And I'm going to go over specifically 7 and 10 to show you different ways of solving. So I'll just get started. Looking at number 7, it says a person is shot out of a cannon at 29 meters per second. Assume the cannon is 4 meters long. Consider only the motion while the person is inside of the cannon. Alright, so we're going to draw a motion diagram, make a list. So I'm going to go ahead and actually start off by drawing a cannon here. I gotta get the cursor over there. Alright, so I'm going to draw a little picture of this. So pretend there's a person inside of this cannon, and we'll assume the detector is right here. And so you know the person, if you're looking at just the motion inside of the cannon, they're stopped, and then they speed up out of the cannon, and then after that they'll slow down. So we're going to look at only the motion inside. So let's go ahead and list our variables. We have our initial velocity, we have acceleration, we have distance, we have time, and then we have our final velocity. So looking at this, our initial velocity is 0 because the object or the person is at a stop. Acceleration we know is to the right. We know it's positive, but we don't know what it is. The distance, the cannon is 4 meters long. And the time, we don't know, but the final velocity, meters per second, remember, is a unit for velocity, and that's what it is at the end when it's shot out. The person is shot out. So then we have the setup, so we have to figure out acceleration and time. Then you have to sketch the graphs. So we're not going to solve using graphs this time. We're actually going to solve using the equations, but I would like you to practice sketching the graphs because you'll have to use this in other problems, especially in the test. So it starts off close to the detector. Remember, the detector is down here, and it goes slow, then fast. So we're going to go ahead and go slow, flatter, and then steeper, fast. Okay, I don't know the time, and the distance I know is 4 meters. Here, the velocity, I know it starts off at 0. It's heading away, so it's going to be positive, and it goes up to 29. So it starts off at 0 and goes up to 29, but I don't know the time. And then the acceleration is, we know, positive, the slope is positive. Horizontal, because it doesn't change. Alright, and I don't know the time, and I don't know the acceleration. So now we have to use the equations to figure it out. Well, not all of them are going to work every time. You got to figure out which one is going to work for you. So looking at what you know and what you don't know, you got to look at what the equations give you. So looking at this, I know the final velocity, I know the original, I know 2, of course, I don't know the acceleration, and I know the distance. So the only one I don't know here is acceleration. So this one could work for me to solve for acceleration. Looking at this one, I know the distance, I know the original velocity, I know the final, and then I don't know the time. So I can figure out the time using this equation. If you look at these all have 2 things you don't know. So you got the V you know, the VO you know, the A you don't know, and the T you don't know. So there's 2 things you don't know there. You can't use this one. Same thing here. There's 2 things you don't know. So we're going to use these 2 equations to solve for our unknowns. So let's go ahead and plug in chug. We got our final velocity to be 29. So we got 29 squared. Original velocity is 0 squared. 2, we don't know the acceleration, and the distance is 4. So we have 29 squared, and then you have 2 times 4, this is just 0 here, so you got 2 times 4, which is 8. A is equal to 29 squared. Got to divide by the 8, and you get your acceleration to be 105 meters per second squared. You should only have 2 sig figs because the numbers here have 2 sig figs. Actually, only 1, excuse me, because 4 only has 1. So you should have 1 sig fig, so we're going to stop around, and this rounds to 100 meters per second squared. So that's quite the acceleration there. All right, then we can go ahead and figure out our time. The distance we know is 4. The original velocity we know is 0. The final is 29. Sorry, it's just not writing very well there. Divided by 2. And then we have our time we're trying to figure out. So what you can do is go ahead and take the 29 here, because 29 plus 0 is 0, and divide it by 2. So you get 14.5 t. And then if you divide by the 14.5 on both sides, you get t is equal to 0.276. And you should only have one sig fig, so that is equal to 0.3 seconds. So I'll make sure your final answers have the correct number of sig figs. So we're just using the graphs to think about the motion, and then we'll use the equations to solve. So remember, there's only can be one unknown in order to use the equation. Okay, I'd like to go over one last problem with you. This one, you're throwing a bag of peanuts. This is number 10, so make sure you change to number 10. You're throwing a bag of peanuts straight up to a friend in a skybox 10 meters above you. Assume that the bag just makes it to the height and that you're on Earth, so good thing to assume. All right, so we have your motion detector, and then you're going to throw the bag of peanuts up. So it's going to go up fast, and then it's going to slow down in time. Okay, so you have your original velocity, you have your acceleration, your distance, and your time, and then you have your final velocity. So the acceleration, assuming you're on Earth, and we figured this out from the drone experiment, you have negative 9.8 meters per second squared. And then the original velocity, you don't know what it is. You launched it up there, you're not sure what. But the final velocity, you know, is going to be 0 meters per second, because it just makes it to that height, so that's where it stops at the very peak of its flight. So at the very top, it stops at 0 meters per second. The distance, he's 10 meters above you, or she. And then the time that goes by, we're not sure about. So we don't know the original velocity or the time. So in the distance versus time graph, it starts close to you, close to the detector, goes fast, and then slow. So steeper than flatter. The time we don't know. We know ends up 10 meters away. The velocity, we know it starts off fast, heading away, and then it slows down to 0, but we're not sure how far up that starts, and we don't know the time. But we know it ends at 0 for sure. And then looking at the acceleration, we know that's negative 9.8 meters per second squared. All right, so we have some things we have to figure out. We have to figure out the original velocity, and we have to figure out the time. So looking at these, the best option would be this equation. We know the final, we don't know the original, we do know the acceleration and the distance. So from here, the only thing we don't know is the original velocity. And once we get that, I'm going to use the easy equation, and you figure out the time with the easy equation. So we got velocity is 0. The original velocity, we don't know. The acceleration is negative 9.8. And the distance is 10. So to solve, we have 0 is equal to the original velocity squared plus a negative 196. And then to get VO squared alone, we're going to add the 196 and take it to the other side. Take the square root. And that will give you 14 meters per second, which rounds to 10 meters per second. So once you have the 10, take it over here, We got our final velocity is 0. Our original velocity we just figured out was 10. And you can use other ones, it doesn't matter. I'm just using this one because it's easy. The acceleration is negative 9.8. And then the time, we don't know. We're trying to figure that out. So we're going to go ahead and subtract 10. And then divide by the negative 9.8 to get rid of it. So then you get your time to be 1 second. Okay, again, you could have used other ones at that point, but this is an easy equation to use, so I try to use that one when I can. So you can see we got all of our pieces here. We got our motion diagram, our graphs are there and labeled, and we showed our work for which equations we're going to use to solve.